So hello guys. Oh, I can introduce myself. So I'm Kim Cedric B. Suinan, a first year college from Laguna State Polytechnic University and a CPE 1B. So I'm here to discuss about the planar graphs and the Euler's formula. So the learning objectives. At the end of this video report presentation, you will able to define planar graphs and plane graphs, identify if the graph is planar or non-planar, define the Euler's formula and its relationship to plane graphs, know the Euler's polyhedron formula, define maximal plane graphs and triangulation, define bipartite graphs and complete bipartite graphs, know the characterization of planar graphs, define the elementary subdivision, edge contraction, and graph minors. And last is to know the Kuratowski's theorem, Wagner's theorem, and the Peterson graph. So, imagine that you take out a piece of paper and you start to draw a graph. Now, maybe the graph you draw looks something like this. And you'll notice that two of the edges cross over each other, and we call that an edge crossing. But you could draw the exact same graph in a different way with no edge crossings. So, we'll do that in this another graph. Now, both of these graphs are the complete graphs on 4 vertices, that is K4. So this graph tells us that K4 can be drawn with no edge crossings. And this leads us into important definitions. A planar graph is a graph which can be drawn in a plane graph without any edge crossings. And next is, a plane graph is a planar graph which has been drawn in the plane with no edge crossings. So in our example, we know that K4 is a planar graph, but only the second graph is a plane graph. Now, a plane graph can divide into regions. So let's take a look at our example again. We have a drawing of K4 which is a plane drawing, and we can label our regions R1, R2, R3, and the unbounded regions or the exterior regions which is R4. Notice that R1, R2, R3 are bounded. They are contained. But R4 is unbounded region. In fact, every plane graph has an unbounded region which is called, I have said earlier, the exterior region. So let's make another examples. So if we draw a triangle, we can see that it is just divides into two regions, the one inside the triangle and the one outside the triangle. And if we make another graph like this tree, the tree graph on some number of vertices, we can see that it is easily drawn in the plane and it has only one region, which is the exterior region or the unbounded region. In fact, it proves that every tree can be drawn as plane graphs and has only one region, which is the unbounded region. The boundary of a region in plane graph is the set of vertices and edges that outline it. So if we look at this example graph, which is a plane graph, and this example graph, which is also a plane graph, we can label the region 1, R2, R3, and we see that although the graph are isomorphic, these graphs are different plane graphs. They have different boundaries. For example, if you were to find the boundary of R2, it will be contained only this triangle, whereas the boundary of the R2 in the other drawing looks different. So note that even though these graphs are clearly the same in the sense of that they are isomorphic, they could be drawn in different ways in terms of a plane graph. So let's make another example. So let's make 3 vertices on top and another 3 vertices on the bottom. The question is, can you connect every first set of vertices in the second set of vertices so that no edges will cross? So in this graph, it is called a complete bipartite graph that will be discussed later. And the name of this graph is K3 tree. It turns out that K3 tree is not planar. So the takeaway is that not every graph can be drawn in a plane drawing. Now let's see why is it K3 tree is not planar. So we notice that K3 tree has a Hamilton cycle. So first, we redraw the 6 vertices and just draw the Hamilton cycle. So here is the Hamilton cycle. And we notice that it has some crossing of edges right there. But what we can do is to redraw that cycle so it doesn't have any edge crossings. So there, we notice that we have the first set of vertices and the second set of vertices, and we now have the Hamilton cycle without any edge crossings. But in the original drawing, we're missing 3 edges because in the original graph, the blue vertex is connected to all the red vertex. And that means if we take a look of that first set of vertices in the Hamilton cycle, it needs to have an edge to go to every second sets of the vertex. So right now, the 2 sets of vertices missing an edge to both of other sets of vertices. So that means we have 3 more edges needs to make to satisfy the original graph. So there, we have 1, but if we put another 1, we can't go across in the middle of the Hamilton cycle without hitting the edge. So dadaan tayo sa labas or outside the Hamilton cycle, and there we go, no crossing, but there's another 1. So kung makikita nyo, kung dadaan yung isang edge papunta sa kabilang vertex to the opposite vertex, it would result of edge crossings. But if we draw an edge outside the Hamilton cycle, it is also stuck or have an edge crossings. So we can say that K3 tree is not a planar graph. So here, let's draw an example of a plane graph. Then let's label it region 1, region 2, region 3, and don't forget the exterior region, which is region 4. Next, we look on how many vertices, edges, and regions it has. So, makikita natin, the green vertices is the vertices, which is 1, 2, 3, 4, 5, 6, 7. Then, M as edges, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we can say that it has 4 regions. Then, if we solve it in n minus m plus r, it is equal to 2. So, 7 minus 9 plus 4 is equal to 2. So, let's take another example. And label natin siya ng R1, R2, and the exterior region, R3. Then, hanapin natin ang N, M, and R vertices, edges, and region. Then, makikita natin na it has 7 vertices, 8 edges, and 3 regions. Now, if we solve it again, the same in the other graph na n minus m plus r, it is equal to 2. So, 7 minus 8 plus 3 is equal to 2. Now, this is not just a coincidence. It is actually holds for every connected graph. So, the theorem that we want to prove is, if G is a connected plane graph with n vertices, m edges, and r regions, then n minus m plus r is equal to 2. So, this is actually known as Euler's formula for plane graphs. So, ano nga ba ang Euler's formula? Euler's formula states that if a finite connected, and plane graphs is drawn in the plane without any edge intersections or edge crossings, and n is the number of vertices, m edges, and r is the number of faces or the regions bounded, including the exterior regions and infinitely large regions, then n minus m plus r is equal to 2. So here is the picture of Leonhard Euler, a Swiss mathematician and physicist, one of the founder of pure mathematics. So sa kanya nagmula ang graph theory that may be specifically traced in 1735 when Euler solved the Königsberg Bridge problem. So dito, gustong malaman ni Euler na posible bang dumaan ang isang tao sa lahat ng bridges na to na hindi uulit sa isang bridges. So it is problem solved by Euler. So para ma-prove ang theorem na to, in general, the proof will use induction on M, the number of vertices edges. The base case is just when M is equal to 0, so you have a connected plane graphs on no edges. So we can say that it's a K1, it is just a dot or isolated vertex. So that means n vertex is equal to 1, m edges is 0, and the regions is just the exterior region. Well, if we solve it in the Euler's formula, n minus m plus r is equal to 2. So 1 minus 0 plus 1 is equal to 2. So now, we use this induction hypothesis to show that the theorem will hold for any connected plane graphs on m edges. Now we consider a connected plane graph G on m edges and n vertices and r regions. Our proof now divides up into cases, depending or not to graph G is a tree. If you know that a graph is a tree if it is connected and acyclic, that means it is connected and have no cycle. Our first case to consider is if G is a tree, then m is equal to n minus 1 and r is equal to 1. So we see this on the previous. In this case, so n minus m plus r is equal to n minus close parenthesis n minus 1 plus 1 is equal to 2. So we substitute m to n minus 1. So if we simplify, n minus n is cancelled out, then negative sign plus negative 1 is positive 1 plus 1 is equal to 2. Then if G is a tree, then it is done. We already know that G is a connected graph. So if G is connected but not a tree, then G must have a cycle C. Now, we'll let E be an edge on our cycle C. Now, our aim is to remove that edge E and apply the inductive hypothesis to smaller graphs G without E. So we need to be careful that if we remove that edge E, we need to make sure that we don't disconnect the graph, because the inductive hypothesis only works only to connected plane graph. So think on E. If removing E will disconnect our connected graph, then E would be what's called a bridge edges, where bridge edges means the edge is a bridge if and only if it lies on no cycle. However, E clearly lies on cycle C, so we took it to belong to cycle C. That tells us that E is not a bridge edge, and therefore the graph without the edge E is still connected, and it has n vertices, m minus 1 edges, and r minus 1 regions. To see why this is, let's have an example. Here in the plane graph, which has a cycle on it, so in this, we highlight the particular cycle, we call that C. Next, we'll highlight some edges of the cycle, we call that E. And if you can see that if you remove the edge E, we will not going to disconnect the graph. Also, it will stay planar. So then, if you notice that if we remove an edge, the edges will goes down by 1. The number of vertices stays, but look at what happened in the number of regions. Removing edge E means that R2 and R3 join into one region. And to sum up, removing an edge of a cycle in a plane graph, it will just decrease the number of regions by 1. Thus, by the induction hypothesis, the theorem holds for the graph G without E. Remember that G without E is connected and a plane graph has fewer than m edges. So we know that its number of vertices minus its number of edges plus the number of regions must equal 2. In the inductive hypothesis, so we solve n minus m minus 1 plus r minus 1 is equal to 2. So, kapag sinimplify natin yan, ang makukuha natin ay n minus m plus r is equal to 2. And therefore, by this principle of induction, the theorem holds for all values of n bigger than or equal to 0. Thus, we know that the connected plane graphs with n vertices, m edges, and r regions will satisfy the equation, Euler's formula, which is n minus m plus r is equal to 2. So, a connected plane graph satisfy this equation. But what about disconnected plane graphs? So, it comes out as a corollary if G is a plane graph with C of G, the connected components, then the number of vertices minus the number of edges plus the number of regions just equals 1 plus the number of connected components C of G. Let's take a look at a small example. So here's a 3 plane graphs. Notice that it has 3 connected components and we start the label. The regions R1, R2, R3, R4, and R5. And we see that it has 5 regions. Now, the number of vertices is 12, edge is 13, regions is 5, and also the number of connected components, C of G, is 3. So, if we solve it together, we see that n minus m plus r is equal to 1 plus C of G is 12 minus 13 plus 5 is equal to 4, which is clearly the same as 1 plus 3. So the theorem does generalize to this connected case as well. Euler's formula is often talked about the context of polyhedra. So here, you can see a polyhedron which happens to be a tetrahedron, and it has 5 vertices, 8 edges, and 5 faces. So we'll write V, E, and F for the numbers of vertices, edges, and faces. We can also draw a graph which looks like a bird's eye view of this tetrahedron, and that's the associated graph to that polyhedron. So notice that it has 5 vertices, 8 edges, and also 5 regions. Notice that in this, the bottom of the tetrahedron corresponds to the region that is the exterior unbounded region in our plane graph, which is R5. So in general, if V, E, and F are the number of vertices and edges and faces in a polyhedron, then V minus E plus F is equal to 2. This is known as the Euler's polyhedron formula. It is a famous formula, so now you know where it comes from. So next, let's make a graph, and notice that it is a planar. But what happens if we keep on adding new edges to this graph while maintaining of its property of being planar? So let's see what happens. So we'll keep the original graph and add all of our new edges in red. We want to keep on adding edges as long as they're not crossing any other edges, and just keep going until we're forced to stop. So this is what happens. We end up with this graph. So if we have a new edge, the graph will no longer be a plane graph. So that it is what is called a maximal plane graph. It also happens to be a maximal planar graph, and this is the plane graph drawing of it. Furthermore, If you look at any of the regions in this graph, you'll see that all of their boundaries are triangles, which is 3 vertices and have 3 edges. Even the exterior region. So, this is also called sometimes a triangulation. So, here's another example, and then we'll add edges until we get a new graph, which is a triangulation of the old graph. So, for example, we can add these edges, and now we're stuck. We can't add anymore, and we have a triangulation. Our original graph has 5 vertices, so we could predicted that after making a triangulation, we could end up with 9 edges, because we know that for maximal plane graph, there is a direct formula in how many edges it will have, based on the number of vertices. So, the term we want to prove is that if G is a maximal planar graph with n vertices and n at least 3 and m edges, then m is equal to 3 times n minus 6. To prove this, take a plane drawing of G with R regions, then notice that the boundary of every region is a triangle. Considering taking a number of edges in the boundary regions R and summing this up all over all regions R in this graph, so we can see in this graph that there are a number of regions and each has exactly 3 edges in its boundary, so sum will equals 3 times R. But now, think about the sum on the left hand side and notice that each edge belongs to the boundary of each 2 regions, so in that sum, each edge counted twice, once for each 2 regions, and that means it is equal to 2m. Now, we have a relationship between R and m. We also know that the graph is a plane graph, so it must satisfy Euler's formula for plane graphs. In other words, n minus m plus r is equal to 2. But now we have a relationship telling what r is in terms of m, so we just plug that in. So n minus m plus 2m over 3 is equal to 2. So multiply both sides by 3, so we get 3n minus 3m plus 2m is equal to 6. Then simplify, we will get 3n minus 6 is equal to m. So you can tell exactly the number of edges that will be in maximal plane graph on n vertices. So a corollary of this result is if G is a planar graph with n greater than 3 vertices and m edges, then m is less than or equal to 3 times n minus 6. So this is true because a maximal plane graph is going to have as many edges as we possibly could have in a plane graph on n vertices. So it makes sense that if you could have any multiplanar graph, it will be bounded above by that number. So let's make a formal proof. We have a planar graph G and we add edges G until the resulting graph G prime is maximal planar and has m prime edges. We know from previous theorem that m prime is equal to 3 times n minus 6 because the number of vertices has not changed, but obviously m is less than or equal to m prime, and therefore m is less than or equal to 3 times n minus 6. So next, we need also to know the bipartite and complete bipartite graph. First, the bipartite graph. It is said to be a vertex set. It can be partitioned into 2 disjoint subsets A and B, so that every edge of G joins a vertex of A with a vertex in B. For simple explanation, let's have an example. So, there are no edges formed between 2 vertices in the set A, and there are not edges formed between the 2 vertices in set B. So, kung makikita natin, ang set A has 3 vertices in each graph. Then, set B has only 2. Then, in the first, 3 vertices are joined to vertices. Then, it is called the bipartite. Then, the second is 2 vertices are joined. then it is not a bipartite graph. Kung makita natin, yung set A, two vertices are joined together. So, it is not a bipartite. So, move forward. A complete bipartite graph is a bipartite graph in which every vertex of A is joined to every vertex of B. It is denoted by K, M, N, where M and N are number of vertices in set A and B. So let's have an example. K32 and K33. So let's notice that in the first graph, three vertices are joined to all vertex of set B on two vertices. So in K33, we notice that the three vertices are joined together in the set B, which has three vertices. The next is, we are going to prove that a complete graph having 5 vertices is not planar, and that a complete bipartite graph with both bipartite sets with having 3 vertices is also non-planar. So let's start with the graph K5. So we also know that if a graph is maximal planar, then the number of edges is equal to 3 times the number of vertices minus 6. And as a corollary to that, if a graph is planar, then the number of edges it has is less than or equal to 3 times the number of vertices minus 6. So we're going to use this bound in order to prove that K5 is not planar. So let's state as a fact that K5 is not planar. And let me remind you that being a complete graph on 5 vertices has just 5 vertices and every pair of vertices is connected by an edge. So let's start to prove by telling that in K5 it has 5 vertices and 10 edges. So let's write this down. This means that n is equal to 5, m is equal to 10. Now, if K5 was planar, then the number of edges m must be less than or equal to 3 times n minus 6. So let's plug it in. So 3 times n, which is 5 minus 6, we get equal to 9. But we already know that m is equal to 10, and it is wrong. Therefore, K5 cannot be planar. So this is a proof that a graph is non-planar. We use an important bound in the number of edges, and now what we want to do is to see if we can do something similar to prove that K33 is also a non-planar. So to start, we're going to derive a similar bound in the number of edges if there is an additional condition in the graph. So in particular, the lemma that we want to prove is if G is a plane graph with n vertices and m edges, and it has no triangles, then the number of edges is at most 2 times n minus 4. So we already know that if a graph G is planar, then the number of vertices is bounded by 3 times n minus 6. But we're saying that if we add the additional constraint, the graph has no triangles, then the number of edges can be at most 2 times n minus 4. So the proof of this is going to be very similar to the proof we saw in the previous, which gave us another bound. So let's start the proof by considering a plane drawing of a graph G. Now, we add edges while keeping the resulting graph, a plane graph with no triangles, until we get to a graph G prime which is maximal with respect to this property. So when I say this property, it means the property that is still a plane graph and has no triangles. So the graph G prime has m prime edges, which is at least as greater than m. And if we consider the sum over all of the regions in the drawing of G prime, and what we're summing up is the number of edges on the boundary of each of those regions. So we will get definitely something that is at least 4 times r, where r is the number of regions. This is because G prime has at least 4 edges in the boundary of each regions. So remember, R here is the number of regions in the graph G prime in its plane drawing. But remember, as we discussed, the sum on the left hand side is counting all edges in the boundaries. So if you're thinking particular edge, it was counted once on one's boundary and another time on other side. So every edge is counted twice. So this means that the sum on left and side is equal to 2 times m prime. And now, we have a relationship between m prime and r. So it tells us that r is less than or equal to m prime over 2. But remember, g prime is a plane graph which Euler's formula holds for it. So this tells us that 2 is equal to n minus m prime plus r. So, and we also know something about r in terms of m prime. So this whole thing is less than or equal to n minus m prime plus m prime over 2. So simplifying it, we get the m prime is less than or equal to 2n minus 4. And now, we know that m is also less than or equal to 2n minus 4. So this tells us that as long as our graph is planar graph with no triangles, we have another bound that we can use in the number of edges. So what we want to prove now is that K33 is not a planar. So let's draw a K33, and it has two partite sets with 3 elements in it. So to start the proof, let's notice that K33 has 6 vertices and 9 edges. And remember that K33 is bipartite and has no odd cycles. In particular, since it has no odd cycles, this means K33 has no triangles. Now let's say if K33 is planar graph, then it is a planar with no triangles. Then we can use the bound that we proved earlier, that m is less than or equal to 2 times n minus 4. Then we plug in n equal to 6, so 2 times 6 minus 4, so we will get 8. But we already know that m is equal to 9, so this cannot be true, and therefore K33 cannot be planar. Now we've seen that K5 and K33 are non-planar graphs, and it is clear that if a graph G contains K5 or K33 as a subgraph, then G is not planar graph. In other words, if your graph is planar, then it is forbidden for having a subgraph of K5 or K33. But the fascinating part is that it turns out that these two graphs, K5 and K33, are the only forbidden subgraphs, and this will lead us in Kuratowski's theorem. Now let's talk about the characterization of planar graphs. So I have said earlier, this is what you call Kuratowski's theorem. So let's talk about what Kuratowski said and build up with it. First, we call that K33 is non-planar and K5 is non-planar. And also, if graph G contains a non-planar subgraph, then G is non-planar. So let's have an example. So here, we have a graph G which is remarkably similar like K5, but have extra vertex and extra edges. But notice that because it has K5 as a subgraph, so this graph G is also a non-planar. Because if we could draw graph G in a planar way and remove that extra edges and vertex, it will end up having a graph of K5. So that means, the statement holds. And if you have a non-planar graph as a subgraph, then it cannot be planar. So let's have another example. Observe that another example here is like K5, but adding a new vertex that interrupts an edge that is in K5. So in this graph, K5 is not a subgraph, but it is still true that this graph is non-planar, and the reason is similar. Because if you could draw this graph in a plane drawing, then you will do is to remove that one vertex that lies on the line and replace it with just an edge. And then you would have a plane drawing of K5. So this graph is also a non-planar. But it is not because K5 as a subgraph. It turns out that this graph G is called a subdivision of K5. So first, let's define an elementary subdivision. So an elementary subdivision of a non-empty graph G is a graph obtained from G by removing an edge E is equal to UV and adding a new edge, vertex W, and two new edges, which is UW and VW. So, if we look at the example graph, we can think of this as a start off of K5. And then we have the edge, U and V. And we remove that edge, instead put in a new vertex, W, and replace it with edges going from U to W and from B to W. So in other words, this graph G is an elementary subdivision of K5. To make sure that we're comfortable with this definition of an elementary subdivision, so let's take another example. So here, there's a graph G which has only 4 vertices, and I'm going to label its M as U and V. Now, an elementary subdivision using that edge is going to say, remove that edge and then put in a new vertex. So we will draw the graph, but now we have that edge removed. Now, we put in a new vertex W and two new edges that goes from U to W and from B to W. So it's look like we added a new vertex onto an edge. Then we define a subdivision of a graph G to be, a subdivision of a graph G is a graph obtained from G by a sequence of 0 or more elementary subdivision. So let's have some other example. So notice that G is obtained from G itself by its 0 by an elementary subdivision. So in particular, a graph G is a subdivision of itself. Then next, we want to take a look at doing an elementary subdivision. So let's have some example. Suppose we do an elementary subdivision on the top edge and we get a new graph. Let's call that new graph G1. So it happens after one elementary subdivision and the new vertex and the new edges. But now, this is just a graph and we could perform another subdivision on any one of the edges we like. So, here G2, we notice that G2 is an elementary subdivision of G1. So G2 is not an elementary subdivision of the original graph G, but it was obtained from two elementary subdivisions. So we call it a subdivision of G. So we can also put another elementary subdivision of any edge we like. So let's make another example to represent G3. So here G3, all of G, G1, G2, and G3 are known as subdivision of the original graph G. And we could make this in many ways, and this is just an example. So observe that any subdivision H of an original graph G is planar if and only if the original graph G was planar. So this makes sense because subdividing an edge does not change the planarity of the graph. So in particular, we know for a fact that K5 and K33 are non-planar. So then we know that if a graph is subdivision of either one of those graphs, it is definitely a non-planar graph. So these facts make perfect sense, but the surprising thing is that graph which has subgraph that is a subdivision of K5 or K33, those are non-planar, but they are the only one that are non-planar. And that fact is known as Kuratowski's theorem. So, Kuratowski's theorem said that if a graph G is planar, if and only if G contain no subgraphs which is subdivision of K5 or K33. Now, it is clear that if the graph has subgraph that is a subdivision of K5 or K33, then it is a non-planar. And as long as it has no K5 or K33 in our graph, then your graph is planar. So now, let us talk about another theorem, which is Wagner's theorem. This is another way to characterize planar graphs. But first, let us define what is graph minor. So step 1, let's define edge contraction. So let's start by looking at an example of an edge contraction. So here's a graph which is the original graph G. And we will contract this edge E. Now recall that deleting an edge would look like just erasing that edge. That would be deleting the edge E. However, when we contract the edge E, what we want to do is to think about the two end vertices of the edge E as just being forced closer and closer together until they become a brand new identified vertex. So we get a new graph. And notice that the end vertices of edge E have now been identified. So the edge E has disappeared, but we have some multiple edges right now. Because the two endpoints and the two end vertices of edge E are both adjacent to certain neighbors, so that we're getting multiple edges in this particular example. So this will be the resulting multigraphs that we get after contracting the edge E. So now notice that any other edges which were not related at all to edge E just remain the same in the same graph. Now since we are often looking at a simple graph, we may wish to consider contracting an edge and then looking just a simple graph that results. So if we go ahead and delete any loops or multiple edges that may have occurred during the contraction, we will get the resulting simple graph after contracting the edge E. So now, if we have a graph G and we contracted an edge E, then the notation we use for a new graph is G/E, a forward slash, because if we use \E, usually it denotes a graph with the edge E removed. So it's very important to keep the notation clear and make sure that we don't confuse the notation for removing an edge with the notation for contracting an edge. So now, let's write down what we did in general for a graph. So in general, let G be a graph and E belongs to the edge E set of the graph. So let also E be equal to UV so that end vertices of E are U and V. Furthermore, suppose that W does not belong to the vertex set of the graph G. Now the contracting edge E in the graph G results in a new graph denoted G/E, which is obtained from G by first removing the edge E, second removing the end vertices U and V, and replacing it with a new vertex W. So if we look back in our example, we see that edge E had end vertices U and V, and in the new graph we replace those with the vertex W. So the third step is to make sure that the vertex W is adjacent to all of the neighbors of U and adjacent to all of the neighbors of V. So that's an idea of an edge contraction. Now we are ready to define what is a graph minor. So a graph H is called a minor of G if it can be produced from G by successive application of this reduction. So first of all, deleting an edge, second of all, contracting an edge, and third, deleting or removing an isolated vertex. So if we take a graph and perform any of these three operations, the resulting graph we get is called a minor, the original graph. Now notice that G is going to be a minor of itself, because if we take a graph and we don't perform any of this operation, so you have a minor. It's just be performing a zero operation. Now, because of the way we may have labeled or represented our original graph, it is important to notice that every graph which is isomorphic to a minor of a graph G is called a minor of G. So, if you have a minor which is isomorphic to K7, then you just say that K7, the complete graph, is a minor of your graph. Now, let's look at an example. Now, suppose you start a small graph and let's pick an edge that we want to delete. So now let's draw a new graph that is the result. And now we have an isolated vertex, and now let's remove that isolated vertex. So next step is to make a new graph. This, we have only 4 vertices, and maybe now, let's perform an edge contraction. So after we contract that edge, the new graph we get has multiple edge, and we need to remove that and only considering simple graphs. So this is the result. Now this is the edge contraction obtained of the graph, which is isomorphic to K3. So that is a triangle. So in other words, we can say that the original graph G has a K3 minor. Now that we define the graph minor, we can state that Wagner's theorem, which is a characterization of a planar graph, is said to be a graph is planar if and only if it has no K5 or K33 minor. So let's compare this statement with the statement of Kuratowski's theorem. So Kuratowski's theorem said a graph is planar if and only if it has no subgraph that is subdivision of K5 or K33. So obviously K5 and K33 are the key parts here. So if we compare these two theorems, maybe the first thing to notice is that Kuratowski's theorem proved his theorem in 1930s and Wagner's proved his theorem in 1937. Now there are situations that Kuratowski's theorem is more easier to use, but there are other situations that Wagner's theorem may be easier or more appropriate to use. Since Wagner's theorem deals with minor and Kuratowski's theorem deals with subdivision, let's briefly discuss about the difference having a subdivision of a graph within the graph and having a minor. So first note that a subdivision of H can be converted into an H minor simply by contracting all but one edge in each path formed by the subdivision process. So let's have an example. Here, we have a K3 which has subdivided twice. So to give a subdivision of K3, we can look at the paths formed by the subdivision process and simply contract all but one of those edges, and we'll end up with K3. So you can convert the subdivision into a minor, but note that H minor cannot be always be converted into a subdivision of H. So kung matatanong nyo, how is it that these two theorems work as both characterization of a planar graph? So we all know that if a graph has a subdivision which has subdivision of K5 or subdivision of K33, then it would also have one of those minors. But how do you know that if you have a minor of one of those graphs, you would end up with having a subdivision of one of those graphs? Well, even though having specifically a K5 minor, it won't necessarily tell you that you have a K5 subdivision. We do know the following fact, or that K5 and K33. For those graphs in particular, if a graph G has to have at least one of those two graphs as a minor, then it will have at least one of those two graphs as a subdivision. In other words, maybe you find a K5 minor in the graph that doesn't necessarily tell you that you will have a K5 subdivision as well. But it does tell you that there will be at least a K5 or a K33 subdivision in your graph. In other words, it will be non-planar. So in general, these two theorems are equivalent. Now, let's have an example in which we can use these two theorems in characterizing a graph if it is a non-planar graph. So, let's talk about the Peterson graph. This is a really well-known famous graph, so you should recognize to this drawing of Peterson graph. So, we need to prove that the Peterson graph is a non-planar. So, let's prove this in two ways. First is by using the Kurtowski's theorem, and second way is the Wagner's theorem. So, proof number 1, Peterson graph contains a subgraph that is a subdivision of K33. Now, it's gonna rely in Kurtowski's theorem. So, in that, it has such a subgraph in going to show that it is a non-planar. But you may wonder, why do we say K33? But it's look like a K5 subdivision. Even though it is similar to K5, it does not contain a subdivision of K5 because K5, the complete graph on 5 vertices, necessarily has every vertex of degree 4. So if you take a graph and subdivide it, you would still have 5 vertices of degree at least 4. And that doesn't happen in the Peterson graph because the Peterson graph is tree-regular. So even it has no subgraph, which is a subdivision of K5, we will show that it does have such a subgraph, which is a subdivision of K33. So first, redraw the Peterson graph, then label it 1 to 10. Then next is, look at the particular subgraph, so varies or just leave as dotted lines, 2 of the edges. So we now look at the subgraph, the Peterson graph, with the edges 7, 8, and edges 3, 4 removed. So makita natin na we removed the edges of 7, 8, and the 3 and 4. So now we look on or search for structure of K33. So we get the color of 1, 9, 10 as the red vertex, then green vertex of 2 and 6, 5. So now let's redraw the subgraph. Now we put the red vertex on top and the set B, which is the green vertex, on the bottom. So kung makita natin na the vertex 1 is adjacent to vertex 2. I said the vertex 1 is adjacent to vertex 2. So, nawala na ang nagle-label sa atin. So, direct. Ba't nawala yung nagle-label? Ano, nakatulog na yung editor? Bakit? So, technical problem, guys. So, let's have a break muna. So, kape muna tayo, guys. So, ayan na. So, ayan, bumalik na daw yung editor natin, guys. So, let's continue. So, one vertex is adjacent to vertex 2. Then, it is adjacent to vertex 6 and also to 5. Then, the vertex 9 is adjacent to vertex 2. Kung makita nyo, dadaan muna siya sa vertex 3. So, lalagyan natin ng path ng vertex 3. Then, it is adjacent to vertex 6. Then, kung makita nyo, ganun din sa 5. So, 9, lalagyan natin ng path ng vertex 8. So, we put path vertex 8. Then, the number 10 vertex, it is adjacent to 2, pero dadaan muna siya sa 7 vertex before going to 2. So, let's put that. Then, 10 is adjacent to 6. Then, 10 is adjacent to 5. But for going to that, it have a path on vertex 4 before getting to 5. So now it is clear that the subgraph we're looking at is a subdivision of K3 tree. So therefore, the Kuratowski's theorem, the Peterson graph, it's a non-planar. So, proof number 2, we need to prove that the Peterson graph has a K5 minor. In other words, we will use the Wagner's theorem in this proof. So, redraw the Peterson graph. So, in this graph, let's use edge contraction. So, label it E1, E2, E3, E4, and E5. So, if we contract these edges, so edge contraction, as we get closer and closer, what we will get is exactly isomorphic to K5. So therefore, by Wagner's theorem, Peterson graph is a non-planar. And we're done. And ayun, binibilangan na tayo ng editor in 10 seconds pero di pa tayo tapos. So okay, bilisan na lang natin. So we can see that Peterson graph is non-planar and we can use two methods to prove it. So in this, we see that Wagner's theorem is easy to use to the Peterson graph. But sometimes Kuratowski's theorem is more apparent to other graphs. So if you're having a particular example, remember that you have both Kuratowski's theorem and Wagner's theorem. So I hope you enjoyed the video and thank you for listening.